Welcome to The Explainer. Today, we're diving deep into a cornerstone of science. I mean, this thing is so fundamental, it literally explains everything, from an ice cube melting in your drink to, the ultimate fate of the entire universe. So, check this out. We're starting with a quote from Albert Einstein himself. And it's a big one. He was talking about classical thermodynamics, and he said he was absolutely convinced that its simple, universal rules would never be overthrown. I mean, think about that. Never. So what is this theory, right? What on earth makes it so powerful, so unshakable, that it got that kind of praise from Einstein? Well, that's exactly what we're going to unpack.
All right, so to really get a grip on this, we've got to learn to speak its language first. It all kicks off with just a few basic definitions that kind of set the whole stage for us.
Okay, first concept, this system. And really, this is just whatever piece of the universe we decide to put a magnifying glass on. It could be super small, like a chemical in a lab beaker, or it could be massive, like the Earth's whole atmosphere. Think of it as the stage where all the action happens. Now, these systems can be what we call homogeneous, which just means it's the same stuff all the way through, like the air inside a balloon. Or they can be heterogeneous. That means they have different, distinct parts or phases. The perfect example is a glass of ice water, right? You've got solid ice and liquid water all mixed together.
We also have to think about what these systems are swapping with their surroundings. So you have an open system. Think of your morning coffee. It's losing heat to the air and steam is coming off it. Then there's a closed system, like a tightly capped water bottle. It can get warm or cold, sure, but the water itself isn't going anywhere. And finally, you have the holy grail, the theoretical isolated system. Basically, a perfect thermos that exchanges absolutely nothing. No energy, no stuff. Zero.
Okay, so now that we've got the lingo down, we can really dive into the heart of it all, the three core laws of thermodynamics. And trust me, these are the unbreakable rules of the entire cosmic game. People have a really great kind of cynical way of summing up these three laws. The first one is, you can't win. You can't create energy out of nothing, you can only move it around. The second law, you can't break even. Because disorder, what we call entropy, is always, always increasing in the universe. And the third law, you can't even get out of the game. You can never actually reach absolute zero, that point of perfect zero entropy order. It's impossible. That second law, the one about everything always getting messier, is probably the most profound of the bunch. It's just so fundamental. So much so that its main equation is literally carved onto the gravestone of the physicist Ludwig Boltzmann. I mean, what a statement. It's a permanent link between entropy, which is S, and all the possible ways you can arrange the stuff in a system, which is W. And the guy who first came up with this law, Rudolf Clausius, he saw exactly what it meant. And it's kind of bleak. It means the entire universe is on a one-way street, heading towards maximum disorder. It's a future where everything is just chaotic and there's no going back. Okay, so here's the big question. If the whole universe is just constantly sliding into more and more disorder, how does anything predictable ever happen? Like, how does a chemist figure out if a reaction is actually going to go? Well, for that, we need to talk about something I like to call the decider.
Yeah, this is the million-dollar question for pretty much anyone making, anything. Will this thing happen all by itself? Are these chemicals going to react? Is this solid going to melt? The scientific term for this is it spontaneous?
And the answer lies in this incredibly powerful idea called Gibbs free energy. We just call it G. What's so brilliant about it is that it juggles two things at once: the energy change inside the system itself and the change in disorder for the entire universe. And the rule is simple. If a process makes G go down, then that process will happen on its own. It is, quite literally, nature's green light. And this brings us to one of the most critical distinctions in all of science. Thermodynamics tells you if something can happen. So, for example, thermodynamics tells us that, yes, a diamond will spontaneously turn into graphite. But, and this is a huge but, it doesn't tell you how fast.
That's a different field called kinetics. And in the case of your diamond ring turning to pencil lead, yeah, kinetics tells you you're going to be waiting a few million years, so no need to panic.
So with these rules in our pocket, we can do some absolutely incredible things. We can build engines, we can create brand new technologies, and we can even start to think with real scientific backing about the ultimate fate of the entire cosmos.
You know, the funny thing is, the roots of all this super profound theory are actually incredibly practical. It all started back in the 19th century with people trying to figure out one thing: how to build a better steam engine. That's it. And this led them to dream up the Carnot cycle, this idea of a theoretically perfect engine. And by studying that perfect imaginary engine, they discovered the absolute limits on how efficient any engine could be. That discovery, it became a huge part of the second law.
And just look at how far we've taken those ideas. Today, these same principles are fueling the absolute bleeding edge of science. I'm talking about things like laser cooling, where we can literally use light to grab atoms and slow them down until they're just a tiny fraction of a degree above absolute zero. Or think about designing new materials, like high-temperature superconductors, stuff that can carry electricity with absolutely zero resistance. It's all built on thermodynamics. But let's circle back to that really stark prediction from the second law. It points to this possible endgame for the universe called the heat death. Just imagine it, a state where everything has reached maximum messiness, maximum entropy. All the energy is perfectly, evenly spread out. There are no hot spots, no cold spots, which means no useful work can ever be done again. Everything, animate, inanimate, would just stop.
This idea of a slow, quiet fade-out really captured the imagination of artists and poets. You've probably heard T.S. Eliot's famous lines. They're seen as a perfect, haunting description of this heat death. It's not some big, dramatic explosion, but a final, silent whimper.
Robert Frost also had a take on this cosmic ending. He framed it as a choice between two fundamental forces: the world ending in fire, which is pure heat, raw energy, or in ice, which is that cold, rigid stillness. Both, in their own way, are expressions of thermodynamic extremes.
And all of this leaves us staring at a final, truly mind-bending paradox. If the entire universe is ruled by this unbreakable law that says disorder must always increase, then how do you explain us? How does something as incredibly complex and ordered as a living thing, as a human brain, pop into existence in a cosmos that's supposed to be constantly running down? And you know what? That question might just be the most profound one of all.